Welcome. Today we're going to be looking at function notation, reviewing concepts of function notation, composite functions. We're going to be introducing the idea of interval notation after looking at set notation and number lines and going back and forth between the three forms. As well, we're going to be looking at linear inequalities and working with inequalities, as well as representing them in interval notation, set notation, and number lines. So if you recall, function notation was introduced to you in grade 11. Prior to that, you were using x and y as your independent and dependent variables. X is always your independent variables, but now in grade 11, you saw that f of x was almost replacing y and became your dependent variable. So you can think of function notation as x being the input that's going into the function, and f of x is your output. So in this example, we're going to let f of x equal 2x plus 3, and g of x is x squared plus 4x, and we want to evaluate f of negative 6. So we're going to take the function f of x, and x, our input is now negative 6. So we're just plugging in negative 6 wherever we see x, and we're going to get 2 times negative 6 plus 3, which is negative 12 plus 3, which is just negative 9. Part 2 is g of negative 3, so now our x value is negative 3. We're putting into g of x, and we get negative 3 squared plus 4 times negative 3. Remember that negative 3 is all in brackets, so it's going to be 9 minus 12, which is negative 3. Okay, so for our second example 2, we are going to let f of x equals 2x plus 3, g of x is x squared plus 4x, and it's asking for what values of x does f of x equals negative 8. So f of x, remember, is like your y value, and f of x in this case is equal to 2x plus 3, so we can actually just let negative 8 be equal to 2x plus 3. And now it just becomes a linear equation that we can solve easily. So we're just going to bring the 3 to the other side. And sorry, this is so messy. I'm using a really small stylus, so that's why. X is equal to negative 11 over 2. You can leave that as an improper fraction. That's no problem. All right, our third example, 2. We're going to let f of x equal same thing, 2x plus 3, and g of x is x squared plus 4x. And it's asking, oh, at least it's going BC. Okay, that's good. For what values of x does f of x equals g of x? So because we want to find kind of the point of intersection between f of x and g of x, so we are going to make them equal to each other. Now remember, when you make two functions equal to each other, you're basically looking for the point of intersection. So now f of x is equal to g of x, and again we can solve this. Just bring everything over to one side. So we're going to get x squared plus 4x minus 2x minus 3 is equal to 0. Now we can collect like terms. So x squared plus 2x minus 3 is equal to 0. This looks like a quadratic equation, and our a value here is 1, so we can actually just solve this, two numbers that multiply to negative 3 and add up to positive 2. Those numbers are negative 1 and 3, so we can factor that. If you don't remember how to do this, I think the next section will review that with you. X minus 1 is equal to 0, or x plus 3 is equal to 0. So now here we can solve. So x is equal to 1, that's one of our solution, or one of our solutions, or x is equal to negative 3. Remember, it's a quadratic, so it's a parabola, and it's going to have two x-intercepts, which are 1 and -3. All right, example 2 is really bringing it. So we have the same functions for f of x and g of x, and now we want to evaluate f of g of 5. So what I like to do with these is start from the innermost bracket and then work your way out, because we want to figure out what the input is before we get the output. So we need to figure out what g of 5 is, and whatever that answer is going to become your input in f of x. So let's find g of 5 first. So g of 5 is going to be 5 squared plus 4 times 5, which is 25 plus 20, which is just 45. Okay, so g of 5 is your input now for f of x. So it's going to be f of 45, since that's what g of 5 is equal to. And now we're just using 45 for f of x. So 2 times 45 plus 3. And that is 93. So you can have as many functions embedded into that bracket, but always kind of start from the innermost and then work your way out so you can get your final output. Okay, last example of this part. We have the same functions, g of x and f of x, and now we want to simplify f of g of x. So we're putting g of x as the entire input into f of x. And so we can actually write it as f of x squared plus 4x. Again, sorry, this is so messy. And that becomes 2x squared plus 4x. Oh, that's terrible. Okay, sorry guys, let me try again. X squared plus 4x plus 3. Now we can just expand and simplify this. And there's no like terms to collect, so that's our final answer. And now we want to do g of f of x. So f of x is now the input into g of x. And so we're going to get g of 2x plus 3. So that becomes 2x plus 3 squared. 4 times x, which is 2x plus 3. Right, so whatever the outside function is, that's kind of like the skeleton, and your input is going to be what's in the bracket. And then here we can expand this, so this becomes 4x squared. You can use that rule for perfect squared, plus, so 2 times 2x plus times 3 is 6, times 2 is 12, x plus 9 plus 8x plus 12. Now collect like terms. So we get 4x squared plus 20x plus 21. So that last example that we just did is known as a composite function. And basically a composite function is when your input is a function in itself. So you are putting one function into another function, just like we did f of g of x and g of f of x. And it's also can be written as you can see here, we have f of g of x. Can also, that's the way we would say it, but it can also be written as this. So whenever you see almost like f of g of x, like fog x, it would be g of f. They would just switch places depending on what's on the outside. The first guy is always in the outside. Second guy is your input. So you can see it like this. Usually you would see it in this format, but essentially putting a function into another function is a composite function. Okay, so we're going to talk about interval notation and some definitions. So there are several ways to describe intervals. We can write the solution algebraically using set notation. So for example, right here, when we have x such that x is less than 8 and x is an element of the real numbers, sometimes you would see the XER in front of the such that, but basically this is saying that you're including all numbers less than 8, not including 8, but anything less than 8 is included. And you have worked and seen set notation since maybe grade 10, definitely in grade 11. We could also display the solution graphically on a number line. This you've seen starting in elementary school, so this is a different interval. But remember, the open circle denotes that it's not included, and the closed circle is included. So if we wanted to write this in set notation, we would write it as XER such that, because it is continuous during that interval, -2 not included, x, and it's 3 is included, so that's why it's less than or equal to 3. Or yeah, x is less than or equal to 3. So the last way we can specify an interval is called interval notation. And this is what we're going to be learning today. So this probably looks new to you. What this means is x is an element of this interval right here. This u is called a union symbol, and it just means it's also this interval as well. And XER you recognize because it's similar to what we've been using for set notation. So the round brackets are not included because infinity is not a specific number, and you can't really have an open circle there, so that just means it's not included. The square bracket means it includes, so it's greater or equal to, or like that there's an equality there. And so here this includes the 1, doesn't include the usually when you write infinity or negative infinity, it doesn't matter, you would use an open bracket. So let's just draw this interval so we can see it on a number line. So we have -1 here, 0, and 1. So what this would look like, hold on, let me find the highlighter. I know there's a highlighter here. So we have there, and now I need to specify what is open circle, what's closed circle. They're both going to be closed. So this is going to be closed, and this is also going to be closed because the -1 and +1 are included because of those square brackets. So that's what this interval looks like. And just for fun, if we wanted to write it in set notation, it would just be XER such that x is less than or equal to -1 and x is greater than or equal to 1. Okay, so for example 1, describe the set of real numbers from -5 to 3 that includes -5 but does not include 3. So in set notation, we can write XER such that -5 is less than or equal to x, and x is less than 3. And remember, it doesn't include 3, so it's not going to be less than or equal to, it's just going to be less than 3. If we want to write this on or show this on a number line, it would look like this, where remember the -5 is going to be circled in, like that's a full circle, and then we have an open circle for filled in circle, that's what I'm trying to say, and then the 3 is going to be an open circle because it doesn't include 3. in interval notation, we can write that x is an element of between -5 and 3. Remember, -5, we're going to have a square bracket because it includes it, and at 3, it's going to be an open round bracket. So for our next example, we want to describe the set of real numbers which does not include 1. So it's every real number with the exception of 1. So we want to write that in set notation. We would write XER such that x does not equal 1, just as you would expect. And then if you wanted to show it on a number line, everything would be filled in except there would be an open dot, an open circle at 1. And for interval notation, it's a little bit more complicated. We have x as an element of, so everything except for 1, that means -infinity to 1. Remember, we want the 1 to not be included, so we're going to have an open round bracket, and this union symbol and, which means and, 1 to infinity. And remember, the 1 on this side has to be open as well, so it's a round bracket, and it's negative and positive infinity, so those are round brackets as well. Okay, so now we're going to describe solutions graphically. So we looked at an algebraic representation of an interval. Now we're going to look at its graphical representation. So we have a graphical representation using a number line. And how would we say this using interval notation? So it looks like it's including everything from -2, not including -2, to 3. So the interval notation would be x is an element of -2. Remember, it's an open round bracket, and 3 is going to be a closed bracket or square bracket. If we want to express this interval algebraically using set notation, we would say XER such that it lies between -2, not including -2, and 3. So we would write it this way. So just to recap the 3 methods that we've been looking at to describe intervals, we have described solution x is greater than -2 and x is less than or equal to 3 using set notation this way, and then graphically using a number line just like this. And now we just learned something called interval notation, which we can now find another way to describe this interval, and it would be x is an element between -2, not including -2, and 3, including -3. So if you've been following along, this is kind of just a recap. All the possible combinations that you can have for interval notation. If an interval is written x is an element between a, b, this way, then you would know that a would be included in the interval and b would be excluded from it because of the formatting of the brackets. If the interval was written as x is an element of a, b with round brackets, XER, then neither endpoint would be included in the interval. So they would both have open circles if you showed it on a number line. If the interval was written x is an element of AB with square brackets, XER, then both endpoints would be included in the intervals, and those would be denoted with closed circles, filled in circles on a number line. So let's do a couple more examples. We want to represent all real numbers from -3 to 2 inclusive. So using interval notation, that would be x as an element of -3 to 2, and you would have square brackets for both endpoints. Now we want to represent all real numbers except -1 and 4. So then you have to split it up. So we're going to have x as an element from -infinity to -1, union with -1 to 4, union with 4 to infinity. So it's going to exclude those points at -1 and 4. Okay, so one last example in this section. We want to represent this interval with interval notation. So we're going to say x is an element of -infinity to -1. Remember, -1 is included. So we need a square bracket and 1 to positive infinity. On a related note to interval notation, we're going to look at inequalities and operations with inequalities. So I encourage you to look at this table in a little bit more depth. I'm just going to skim over it quickly, but essentially what it's saying, it's giving you an inequality and then it's performing an operation. So for example, for the first one, we have -2 is less than 5. We're going to add 3 to both sides. The left hand side turns into 1, the right hand side turns into 8. That inequality is still true. So whatever you do to one side, you're going to have to do to the other side. So it's exactly like working with equations. Working with inequalities is almost identical. And then we have a few more examples where that's showing you that that's true. Even when we get to multiply both sides by 2, multiply both sides by 2, you'll still get the same inequality to be true. Where it becomes false, if you look at the last two examples, you're going to multiply by -2 or divide by -2. Anytime you multiply or divide by a negative, the sign is going to switch. So that's where it's a little bit different from equations. If you multiply or divide by a negative value, the alligator symbol is going to switch sides. So greater than becomes a less than becomes a greater than. All right, so let's do an example. We're going to solve -3x plus 1 is greater than -8, where XCR. Write the solution using interval notation and illustrate the solution on a number line. So if we are working with this inequality, we want to isolate x, treat it as an equation just like you normally would, unless you have to multiply or divide by a negative. So we are going to first move the 1 over to the other side, and we get -3 is greater than -9. And then we can divide both sides by -3. And remember, when we do that, the sign is going to switch, so it's going to be x is less than 3. And this is what it would look like on a number line. Okay, we got a couple more examples. Solve -4x minus 1 is less than or equal to 2x plus 5, or XCR. Write the solution using interval notation and illustrate the solution on a number line. So same as we were doing before. Let's bring all our values, our numerical values, over to the left-hand side. So I'm going to have -1 minus 5 is less than or equal to 2x plus 4x. I'm bringing my variables to the right-hand side. You could have gone the other way, totally up to you. And that becomes -6 is less than or equal to 6x. And now we are not dividing by a negative, we're dividing by positive, so the signs are going to stay intact. And we have -1 is less than or equal to x. So we can write this in interval notation. X is an element of -1, including -1, to infinity. And we can also show this on a number line like this. For example 3, solve -1 is less than 4 minus x over 2 is less than 3 XCR. So just to get rid of that fraction, we're going to multiply each term by 2. And remember what you do when you have a double inequality, whatever you do on one side, you have to do on all 3 sides. So we're going to multiply everything by 2. We're going to get -2 is less than 4 minus x is less than 6. And then we want to move the 4 over. So we're going to get -6 on the left-hand side is less than -x is less than 2. And now we want to divide by a negative, so we have to do that on all 3 sides. We're going to get 6 is greater than x, which is greater than -2. So notice the alligator sign switch now. And now, because we have a double inequality, you can actually split this up into 2 inequalities. So your first one would be x is less than 6, And the second one would be -2 is less than x. And so we can write it as -2 is less than x is less than 6. That's your final answer. And that would be the union of those two solutions. In the interval notation would be x as an element of -2 to 6. And the number line would look like this. Okay.